This is my solution to chapter 11, number 41. Now, before we start, I want to tell you that this problem is actually quite difficult. And so even if you had some problems with this, I think that that wouldn't be that surprising, but it is solvable, okay? But you need to know a couple things. So one of the things is, looking at the problem, it says that this is a construct where this hoop here is attached to this axis, and this this wire square here is also attached to this axis. In my picture, they don't look like they're attached, but you got to use your imagination. So some things you need to know right away is that we want to find the total moment of inertia. So we use I for moment of inertia. So if we want to find the total, it's going to end up being the moment of inertia of this hoop plus the moment of inertia of the square. Because if you want to find the moment of inertia of two objects that are connected, you just add them up. This idea that you could just add them up is going to be useful. That's how we're going to find the moment of inertia of the square coming up. But let's do the hoop first. If I want to find the moment of inertia of the hoop, one of the things I have to realize is that this hoop isn't pivoted through its center of mass. Its center of mass would actually be here in the center because we want to rotate it this way, not through the center, but through the center this way. And so the moment of inertia for the hoop is we're going to use something called the parallel axis theorem. Okay, it's the moment of inertia through the center of mass of the hoop plus this term, which is mh squared, where h is the distance from the center of mass to the new pivot point. So let's just talk about this construct for a second. Right now we have a hoop, and our hoop, instead of pivoted through the center this way, we're referencing it pivoted through the center like this, where it would be rotating like that. The I through the center of mass for the hoop is actually equal to 1/2 mr squared. That's something that I just looked up in the textbook. It's right there. It's not that big of a deal. But now, where are we pivoting it? We're pivoting it right here. And so the question is, what is this h distance? Well, if you look closely, it turns out this h distance is an actual radius, which is actually going to make this thing pretty easy. So if I take this idea here and move it down, I want to get the moment of inertia for the hoop. I'm going to need the moment of inertia through the center of mass, which is 1/2 mr squared, plus this term mh squared, where h is the radius. And this is 1/2 mr squared, this is a full mr squared, and if I add those two things together, the moment of inertia for the hoop is equal to 3/2 mr squared. So what about our square over here? Well, the square is actually a little bit more difficult because it has 4 parts, and I'm going to label them. I'm going to do it a different color here. This part closest, we're going to put number 1, this is 2, this is 3, and this is 4. And so to get the total moment of inertia for the square, I'm going to take the moment of inertia of part 1 plus the moment of inertia of part 2 plus the moment of inertia of part 3 plus the moment of inertia of part 4. So let's just see what it looks like. The moment of inertia of part 1. Well, if you look at part 1 is actually at the pivot point. And if you're at the pivot point, then your R value is 0, regardless of what it looks like. Your R value is 0, so therefore it's 0. What about number 2? Well, if you look closely, if I just isolate number 2 is attached right here, and so if I just look at number 2, it's a thin rod pivoted at one end. And if you look that up, a rigid rod pivoted at one end, what we found out earlier is that it's 1/3 ml squared, And if I look at the diagram here, our L value is an R, so it's 1/3 mr squared for number 2. Number 3, what I look at for number 3 is, because it's vertical here, it doesn't have any horizontal orientation, therefore it actually acts like a point mass. And so, acting like a point mass, it'd be mr squared. In this case, the R value is the actual R value. And what do I see about number 4? Well, if symmetry is my friend, 2 and 4 should be the same. So I have another 1/3 mr squared. And so if I want to get the total for the square, I'm going to add them up. I have 0 plus 1/3 mr squared plus mr squared plus another third so this is 1/3, this is 1/3, this is 3/3 for a total of 1, 2, 3, 4, 5. So the total moment of inertia for the square is equal to 5/3 mr squared. One thing to notice is that it says the whole hoop has mass m and each little segment also has mass m. So keep that in mind. That's why each of these was an mr squared individually. So let's see where we're in the problem then. I have the moment of inertia for the hoop, 3/2 mr squared. I have the moment of inertia for the square. Let's add them up and see what I end up with. The hoop was 3/2 mr squared. The square was 5/3 mr squared. So this is 3/2 and this is 5/3. This is, if we go common denominator 6, this looks like to be 9/6 mr squared, and this is 10/6 mr squared. So the total and in the problem they give us some values actually. I didn't write them in, but it tells us that trying to find it, hold on. The radius is 0.5 meters. And m is equal to 2 kilograms. So if I plug that in here, I have 19/6 times 2 times 0.5 squared. And that turns out to be, I got about 1.58, we'll call it 1.58, and that's kilograms times meters squared, because it's mr squared. So that's how to get the total moment of inertia. Straightforward enough, but you had to know the parallel axis theorem and the fact that to get the total you just add them up, and you had to do a little bit of thinking over here, which was not super obvious. The second part of this problem says find the angular momentum about that axis. All right. So if you want to find the angular momentum of a rigid object that's rotating, one thing you can do, if you want to find the angular momentum, so angular momentum, we're going to use L. Now linear momentum is mass times velocity, so angular momentum is I omega. One thing that it tells you is that it tells you that it makes one rotation in 2.5 seconds. So is any of this the angular velocity? And it's not, but you can get it from there. Angular velocity tells us the change in the angles over the change in the time. Well, if I did one rotation, how many radians is that? Turns out it's 2 pi radians, and the time it took was 2.5 seconds. So if we calculate that out, it's about, here, I'll get a better value for it. Sorry, hold on. So it's 2.51, and this is going to be radians per second. So if I have that, and I take my total moment of inertia from before, I have 1.58 times 2.51, and my total here is then looks like it's right around 4. Now, what are the units for this? It's kilograms, meters squared, and then you would do radians divided by seconds, but they never put the radians in unless we're talking about that directly. So there you go, chapter 11, number 41.